Okay. Good morning, everyone. Can you hear me okay? I can hear me, but then I'm standing in front of a speaker, so I've got an unfair advantage. I know I'm between you and lunch, so I'm going to make this as long and drawn out as humanly possible. My name is Simon Stewart, like it says in very, very small type down at the bottom there. I am a software engineer at Facebook. I've been there for about 2.5 years now. I joined when we opened the London office. And I am here to talk to you about ludicrously fast builds with Buck. I will explain what Buck is. I'm sure you all know what a ludicrously fast build is. So, before we go any further, I thought it would be quite nice to get some audience participation. I know that makes people feel incredibly happy. If you're sitting on the front row, don't worry, this is for everyone. So, it's a talk about build tools, the world's most exciting things on the planet. But here's why they matter, right? Have you, just raise your hand, right? Have you ever run make clean or ant clean or maven clean in order to fix a build problem? Yes, we all have. And that's because all build tools are rubbish. Have you ever gone to lunch because your build takes so fantastically long? Yes, we all have. Out of curiosity, does anyone think their build is fast enough? I do. Okay, we're very, very lucky people.
Integration tests are incredibly slow, so it doesn't really matter.
Okay, your integration test is slow. So you can have a leisurely lunch with dessert and a couple of pints, a chance to catch up with the family and the kids, go to bed, have a nap, come in the next day. Oh, look, they're nearly done. Has anyone ever been puzzled why a seemingly unrelated part of your system rebuilds after a so-called simple change? Yeah, or worse, why something you've typed some code and you've done a rebuild and like nothing has happened, and you're going like, I have no idea why that's happening. All right. So build tools are awesome. Fortunately, we live in the future. The future is a wonderful place to be, I think we can all agree. We haven't got our jetpacks, we haven't got our hoverboards, but we do have multiple cores in our CPUs. Like, I remember my first computer having like more than one core available to it. And it's like, wow, I can literally multitask now rather than sort of single-threaded multitasking where it would just do task switching faster than I could do. And it's like, that's really clever, and nothing uses it. We've managed to eliminate rust in our laptops and replaced it with sand in the form of SSDs. Fantastic. The spinning disks were fantastic, right? Because you could read stuff very easily as long as it was sequentially. But random access reads were incredibly slow. Writes were amazingly slow. It was all rubbish, right? But, that's unfortunate because doing a build is effectively an exercise in random reading and writing. Yeah, that's good. Gigabytes of RAM. 640K wasn't enough for anyone. 16 gig isn't enough for anyone either. We all want more, right? But, nowadays, this laptop that I'm presenting off here, has a lovely SSD in it. It has 16 gig of RAM. It has 4 physical cores with hyperthreading enabled, so 8 cores available to me, right? So, this is a powerhouse of a machine, right? I would kill for one of these as a developer workstation, even going back 3 years. Storage is not only fast and great at random access, it's incredibly cheap. Like this, the price of spinning Rust dropped through $1 per gigabyte ages ago. SSDs have plummeted through that as well, right? Storage is cheap, it's plentiful, it's fast, it's wonderful. And if the storage locally isn't good enough, networks are going faster and faster. The next generation of Wi-Fi is going to be, almost gigabit speed. If you're on a wired network, it goes, at gigaspeeds, tens of gigabits. If you're on the correct machine and the correct kind of Wi-Fi network configuration. And we've finally done away with normal source control, and we have distributed version control systems, DVCSs, up the wazoo, which is hilarious, right? because now we do lots of branching and merging and pulling from random places, and it's all very exciting. And what that means is that the M time of our files is hopelessly rubbish as a mechanism for determining whether or not a file has changed and therefore needs a rebuild. So we live in the future. Our build tools live in the past. This is the reason why we have these problems that we have. They're task-based. What they need to do is they need to jump through a whole bunch of hoops in order to figure out what they're going to do. So, even if you're using, if you're using something like Ant, does anyone still use Ant? Like a handful of people, right? So it's cool. Ant was a solution. Ant was actually really nice, right? Because you go back to Make. Make was fantastic, right? But it expected one output per input file, right? And Java just went gleefully, like, hey, multiple outputs per Java file. Like if you've got an anonymous in a class, like, fuck you, Make. Presumably that's what it said. I wouldn't know. So Ant was a huge step forward, right? That was fantastic. What it allows you to do is it's like do some Java compilation, just output everything into this directory here, and then jar up everything in that directory here, and we'll call that a build, right? And then when you reran it, and Maven does this too, and Gradle as well, what they do is they stat each of the Java files, and they go, and they look for the class file, and they go, and then if they notice something has changed, then it goes like, hey, here we go. I was talking to a guy who worked on Chrome the other day. This is easy to slow down a build, get an incorrect build using tasks. And what they did is they had a thing that ran find to figure out what files needed to be included for the next step, and it would set up the tree. The person who wrote the build file expected that find command to be run midway through the build, but of course the way their build system worked, it ran right at the beginning. So on a clean build, this directory was always empty, and so nothing happened. And it took them a while to figure it out. Task-based builds are kind of rubbish because in order to figure out whether or not you need to do something for the build, you need to ask every single task whether or not they do it. That's why no-op builds and things like Maven, Gradle, Ant, Make take time, because it basically runs every single task and goes like, do I need to do anything? Do I need to do anything? I don't. Fantastic. I've spent 10 minutes of your time not doing anything. Normal build tools are hard to parallelize. I think in Maven, probably the best you could do is parallelize at the module level for a multi-module build. In Ant, good luck. You've got the parallel tag to indicate that you want to have no idea what's happening right now. Make -J10. Like, if your build works successfully with that, you're a very, very lucky man or lady. And build tools tend to use mtime for hilarious results. Like, this is like 9 times out of 10 the reason why you do like a git pull or a subversion up or a p4, whatever it is, to ruin your source control current tree, your working directory. And it'll update the mtime, and now a built artifact will have a newer mtime stamp than the source thing, which has just changed. And therefore your build system goes, I don't need to do a build. And you're going, yes, you do. Yes, you do. That thing has literally, I've just seen it change. And it goes like, no, not going to do that. It's all rubbish. What could we do? Like, if we were going to design a build system for the 21st century, one to run on your lovely fleet of incredibly powerful laptops and machines and in your data centers on AWS and whatever it is, right? How could we take advantage of these amazing facilities that we have to us that they didn't have in sort of 1997 when they were originally writing Make? Well, modularity is kind of important. We just saw the talk about Java 9's module system, or I did. It's excellent. If you're watching this at home, by the way, go and watch that talk, because Java 9 modules are going to be good. So, what about a build file per package, right? So, at the moment, with lots of build systems, what you need to do, if you want to create a new sort of deployable unit, a new jar file, what you need to do is you need to have like a huge great schlep boilerplate, right? You've got to have like a top directory, maybe a pom.xml or a build.gradle or whatever it is, and then a source main Java, source main test, source main resources, and then you have all your bits and pieces, and then you have like new package name. Well done, lads. Does anyone enjoy setting up that boilerplate? None of you are masochists. I'm very pleased to see this. It would be nice if what you could do is avoid that boilerplate entirely. And so, if you had a build file per package, you could have a single source tree. You could go back to what we used to have back in the day, right, of like source and test, or Java and Java test, whatever you want to call it. And the advantage of a single source tree is it allows for easy sharing of code, discovery of code, and therefore reuse of other people's code, right? At Facebook, we have a single tree for all of our Java code. So, you check that out, and you've got the source code for Messenger, the Android app, FP4A, all the little utilities that we have, Shots, Instagram, you name it. It all lives in a single tree. And we're able to do that because we've got a build file per package. Some people like microservices. Microservices, hot, trendy. Yeah, there's a couple of people going like, I like to decompose my systems. I like decomposing systems. They smell great. There we go. Sorry, that's it. That's the only joke about things decomposing in the entire talk. You can have a single source tree and still have microservices, right? How you organize your source code isn't necessarily how you deploy your executables, your artifacts. Right, those two things are completely separate, and marrying the two because you're not familiar with like how to tease these things apart seems like a less than optimal solution. So a build file per package, that would be nice. And build semantics, right? Wouldn't it be nice if your build system understood what it was building rather than the series of steps it needed to do, right? When you're writing your Maven build files, your Gradle files, your Ant, your Make, whatever it is that makes you feel happy these days, you tend to put the individual steps, right? But you know that actually what you're doing is you're building a jar file, you're building a Java library, you're building an Android library, you're building an Android binary, right? So what if the build system encoded the things you were building at that semantic level, right? That sort of step up from where you are right now. We could call each of these things a build rule, right? So a build rule for a pre-built jar, or a build rule for a Java library, right? And then you could tie everything together. You could express dependencies between rules, right, rather than the individual files within those rules, right? So you could think at the semantic level. You could think of the components that your system is made out of rather than the individual moving pieces. Like, this is why we did object orientation years ago. Right? We did object orientation because the human brain has a sort of limited capacity because we haven't yet hit the singularity. And because we have limited capacity, it's like, well, I can't reason about all the fine details and the larger things. So let's encapsulate some of the fine details in these things we call objects, and then that allows us to think about, reason about the system at a different level. We could apply that same idea to our build tool. That would be nice. If you do that, you end up with this thing called a directed acyclic graph, right? This module depends on that module, depends on that module. Circular dependencies get you into a world where you can't ever compile, right? Which is why it's an acyclic graph instead of just a graph. And here's an example one. Hopefully you can all see that. That says there's an Android binary, and the Android binary depends on a Java library, and that Java library depends on a pre-built jar. So, for example, the pre-built jar might be something like Guava from Google, Java library might be your code, and the Android binary might be, hurling birds for Android or whatever it is that you're working on right now. This is what you might refer to as a target graph. Right? This is the sort of naive representation of what you wrote in the build files. If you were to take all these build files that you've put at the package level and you were to draw lines between them, and you pretended that the whole thing was in a horrific mess, you'd end up with a graph that might look a little bit like that. Once we've got the graph, however, we can transform it into the things we're actually going to do. In the case of an Android binary, for example, it doesn't consume a .jar file, which presumably is the output of a Java library. It consumes dexes, right? And so on and so forth. So you end up with an action graph, right? This is the graph of things we are actually going to do. You can see here we've still got the Android binary, but in this case it depends on two dexes, and the dexes are generated from the Java library, and the Java library still depends on the pre-built jar. So there's a couple of nice things that fall out of this, right? Now, because we're using a graph, it's trivial to parallelize, right? You just do a topological sort, you order by dependencies, you could bucket even by the list of dependencies, and then you can just use a core per build rule, right? So we're going to construct our action graph out of these build rules. Because it's a graph, we can parallelize easily. Human beings don't need to be involved in that process, and that's good because human beings are rubbish. I know we're all perfect, right? But we've all worked with people who aren't. And so that would be really nice, right? And you've got this sort of fantastically fast, elegant build composed of all these wonderful pieces. And so we've solved the problem of parallelization, doing an efficient build, organizing things. But I don't think we've yet solved the problem of I made a change or I did a git update, git pull, and it's not doing a build correctly. So how would we know whether or not we needed to execute each of these build rules in the action graph? Well, we could calculate a rule key, right? If a build rule was a pure function, like functional programming is a new hotness, right? By the way, functional programming is a new hotness, right after JavaScript, Node, microservices. What else is hot? There's a whole bunch of things. Containerization, Docker, Kubernetes, AWS. So there's this list of incredibly hot things, but on that list is functional programming, I promise you. A pure function is a fancy way of saying that given the same input, you always get the same output. So addition, you could think of as a pure function. 2 plus 2 is always 4, unless you're dealing with my 3-year-old, where it could be a random number. So if you treat a build rule as a pure function, what would you need in order to be able to go the inputs haven't changed, right? We could generate a hash. What would need to go into that hash? Well, obviously, going back there, the things that went in, the dependencies are going to be crucial, right? So we'll add the rule key of all our dependencies. Fairly simple, right? Except we have, of course, forgotten the inputs to the current build rule that we're executing, your Java files. We know that looking at mtime is a really bad idea. If you've forgotten why it's a bad idea, then continue getting incorrect builds, and I will sit there and laugh. Far better would be to take a SHA-1, a hash of the contents of the input file, right? So we'll add that into our hash. But that's not enough, right? Because there are different things that could change the output of something. So if you've got a Java library, well, the rules, the flags that you pass in are going to change it. If you have debugging enabled, if you have optimization, if you have a particular class path enabled, whatever it is, right? So the flags are going to be important. And of course, we live in a world where there are multiple different compilers. God damn it, compiler here could give you different output over here, right? So you need some way of going the compiler version, right? But that's not enough. Has anyone here ever had a problem where the thing worked on their machine but not on someone else's? Yeah.
Only in production.
Only in production. That's it. I mean, of all places, it's probably the best place, right? As long as it works in production. It was working in production. It wasn't working in production. Oh, dear. That sounds like a really busy day. Yeah, so, I mean, we've got to take into account, and normally it boils down to someone's done something with their path or their LD library, So there are key environment variables that feed into this, right? So I think we've basically got all we need for the rule key, except we update the build tool from time to time, and that changes the way that we build things. And so you want to encode the build tool version into this rule key, right? And you can think of the rule key as being a hash of this function, right? So the Java library is a pure function. We've generated a hash for it, right? And now we can figure out whether or not we need to execute this build rule by just going like, has the hash changed? If it hasn't changed, then we'll just skip it, right? There's no need to do anything if the inputs haven't changed. And that's kind of nice. And it turns out, if you have this sort of this rule key, this hash, you've built a content addressable system, right, for the outputs of each of the build rules. And you could store that. You could use that as a key to a cache, right? So you could have a massive distributed cache, and you could use the rule key as the cache key. If you find a collision in like the SHA-1 space, which is what we use for rule keys, write a paper about it, because you'll be famous. That'll be nice. So we did some work at Facebook, and we took a look at how our builds were being done and things like that. And we noticed that, on average, only about 3% of each build was unique, which meant that every time someone was doing a build and they weren't pulling from some sort of distributed resource, 97% of that was repeated wasted work. Computers are very good at repeated wasted work. This is why we make them mine Bitcoin for us. But it seems a bit like redundant. We could slash our build times by doing that. And so what we did is we built local and distributed caches, and that helped slash build times. So that's nice. And the key into those caches was the rule key. The nice thing with using a distributed cache, by the way, is that the bigger your engineering organization and the larger your code base, the better this works. You're far more likely to have hits. So as your organization gets bigger, a build system like this and a mechanism of using caches like this works fantastically. It's one of the few cases I've seen where the bigger the engineering organization, the more efficient it becomes. Very weird. So, I mean, it would be kind of nice if we had a build system like that, right? And fortunately, we do. I wouldn't be standing here if we didn't. I certainly wouldn't be giving this variant of the talk if Buck didn't do exactly this. Buck is open source. It's about a year and a half open source now. You can go to www.buckbuild.com if you want to have a look at it. It's on GitHub. It's under the Apache 2 license. It's great. I've been really lucky. I've been working at Facebook, and this has basically been something I've been contributing to since I arrived. And the reason why we wrote it is because back in the day, the Android builds at Facebook used Ant because Google said Ant is the way to build software. Thanks, Google. And the build was fantastically slow, like amazingly slow. Like, good Lord, I can't believe how much coffee I've had today. I'm feeling slightly nauseous slow. And so Michael Bolin, the original author of this, put this together at a hackathon and released it. And put a little call to arms at the beginning of the Ant build. So when you write like ants, build the main Facebook app, there'd be a little message saying, go to this URL, check this out, build that using Ant, ironically. Put this command on your path, cd into this directory again, run buck build target, and completing all those steps, including the checkout and the build of Buck itself, and a fresh build of Buck after modifying a path. That Buck build would finish before the original Ant build had finished. It's ludicrously fast, right? There's nothing quite like a demo. So this is a demo. What you can see here, I've been told not to go in front of the screen because otherwise I'll disappear entirely and be blinded. In the top window, you can see where I'm going to be executing builds. The bottom window on the left is us changing the toast of the Messenger app, and this is the Messenger app deployed over on the right-hand side, up and running. You can see that currently the toast, when you start it up, says hello world. What we're going to do is we're going to run this. Yep, excellent, it's going. We're going to change hello world, and we'll change the toast to be hello everyone. You are everyone. I just like releasing products, right? It's like, yeah, we released it to the world. We're going to do a Buck build, and we're going to install it on our device, right? So this is the Messenger app. It's one of the largest apps in the App Store. And that was a complete redeployment of the application with the new toast and a complete build of it. Obviously, I could have had that. That was so fast, right? I could have stored that in the background. So everyone isn't a proper noun. It should be lowercase e, so I'll just update that. I'll just quickly reinstall it. And there you go. So that's how fast a build using Buck can be. And that wasn't just a build, that was shoveling bits onto the emulator as well. Now, the ADB tops out at about, like, I don't know, a megasecond or something like that, 2 megaseconds. It's not particularly fast. So if you've got a large APK, that takes a really long time to go onto your device. So, like, how do we do this, right? Well, part of it is we built up this directed acyclic graph, and we did all sorts of clever things. We also have a technology called Exopackage, which makes it really, really easy for us to do this kind of thing. I will cover that in a bit. So I said that you have these sort of configuration files at the package level, right? What do they look like? Well, they look like this. They're called build files. They're typically called Buck in shouty case, or Buck, I guess you'd imagine it. Here we have two things. We've got Java binary up at the top, Java library. Java binary is obviously a build rule that we were talking, and its type is Java binary. We have a target defined in the same build file. You can tell it's a target because it begins with a colon. Right, the colon says, hey, look, this can be found somewhere in here. There'll be a thing called example. Example is a build rule of type Java library, and you'll see it's got the name example. All build rules have a name, so all build rules are addressable like this. Obviously, not all build rules are going to be in the same build file, and so there's a mechanism for describing a target defined in another build file, and that is prefixing // which means from the root of my project, there is a directory called third-party guava. In that, there'll be a build file. In that build file, a Buck file, there'll be a target whose name is guava, right, which is probably of type pre-built jar. The other thing here is you don't need to list your sources explicitly. You can just glob them using standard shell globs. You could list them out one by one if you were, that way inclined. And finally, all targets have visibility, right? This allows you to take a build and segment it in a way that allows your teams to keep control of the bits that are private to them and implementation specific, and only expose those APIs that they actually want people consuming, right? If you've got multiple different repos, if you have multiple different modules, this kind of thing is a bit easier to do. But there's nothing to stop someone who depends on your module from depending on any class within that module, up to Java 9, as we found out. With Buck, the build system prevents that. You need to explicitly grant permission to people to use the classes and methods listed in that. So that's a mechanism to allow you to expose like a public contract to your code to the outside world. There is a magic visibility of public in shouty case, which means like, I don't care, anyone can see this. It'll all be good. It'll be fine. That'll be nice. So that's what a build file looks like. If you're thinking that looks a little bit like Python, that's because it is. We actually we run a little Python script to generate everything. So you actually have the full power of Python to do these things. It's advisable not to be too crazy because these are read at parse time and you want parsing to be incredibly fast. All right, but if you needed to, you could do fancy, clever things. And we've used that feature to sort of either wedge in default dependencies to things so you don't need to list particular bits and pieces, or create our own pseudo build rules that look like build rules but really just expand into a set of different things. So, build files, they're nice and easy. I'd like to think they're a bit easier to read than XML. I've never really got along with XML. I quite like things that are easy to read. One of the other things that we have is buckd. Who here runs Unix or a Unix variant? So you're all familiar with D being an abbreviation for a daemon, like a long-running server process, effectively. We make use of another open source project called Watchman. And what that does is it keeps a careful eye on the file system. buckd stays resident in memory. And when you do your build, it first goes to Watchman and goes like, have there been any changes since the last time I did a build? And Watchman will go like, well, this subset of files have been updated. And so we know that we only need to do a certain amount of work because we already know that chunks of this tree are going to be exactly the way they should be. So buckd uses Watchman, caches the target graph. So the first build is going to be slow. The second build is going to be incredibly fast because everything is already going to be resident in memory. And as Watchman tells us that things are changing on the file system, particularly your buck files, we invalidate subsections of the target graph. The nice thing that this gives us is that your initial build time, the parse time, scales linearly with the number of files that have changed rather than the number of files in your repository. So if you have a mono repo where you have literally tens, hundreds of thousands of files in there, your builds can still be incredibly fast because it's only the files that have changed that are affecting your build. That's a really nice property to have in a build system, by the way. Yeah, we like that. So buckd, it's the hotness. Is anyone here running Windows? Okay, a handful of you are. We haven't got buckd running on Windows yet because it uses Watchman, and Watchman requires a bit of work, but it's coming, as is buck support for Windows itself. It's still a bit rough around the edges because all of us use like Linux and OS 10 and things like that. But, if you're going to be a build system, you've got to work on Windows, right? More and more of it does work, so come and have a chat if you're thinking about it. The other thing we can do is, lots of us program in Java, right? Java is a fantastic language. It basically does dynamic linking. It doesn't do the static linking at build time. It basically waits until you load everything up, and then it tells you you've got your class path horrifically wrong. The way that Java does this is it has this thing called the Application Binary Interface, or ABI. And we could take advantage of the ABI in order to minimize the amount of rebuilding that we need to do, right? With a traditional build system, if you modify something fairly high up in the tree, like a utility library that's used by every single module, right, the entire world has to be rebuilt, right? And that's a slow and tedious thing, I think we can all agree. The Java language specification, the JLS, defines what the ABI is. Effectively, the ABI for Java is any non-private class, method, field. The methods are there, but not the method parameter names. The parameter types are stored, but not the parameter names. And obviously, the bodies don't contribute towards the ABI at all, so you could change them. If you were to take a look at this, we could do the ABI. Buck calculates the ABI of everything that it builds. So if it goes like, my inputs have changed, I should do a build. It then goes like, but do I actually need to do a build? So it calculates the ABI of its inputs. And if the ABI has remained stable, using the same sort of hashing mechanism. If the ABI has remained stable, it goes like, I don't need to do a rebuild, and skips that bit. And we log that. And keys rebuilds off dependencies off that, right? Obviously, packaging rules will always be rerun. So if you've got a Java binary and Android binary, you change something, you don't want the whole build going like, nothing happened, nothing happened, nothing happened. Your binary's still the same, right? It'll repackage things for you. So here we've got class foo that has private string, some field, a public method, do something number of times, and it prints the word wow on standard out. Clearly, the first thing that we should tell you is that the cake is a lie. That's a very old joke, but I use it anyway. That was a private field, right? Private fields don't contribute towards the ABI. The ABI remains the same as before. The hash remains the same as before. And therefore, we don't need to do a rebuild. That's kind of nice. So if you're a utility library, you realize that you'd misspelt the word process to like precess or whatever it is, and you just fix that in a variable name. Your rebuilds don't happen. Next thing, times is obviously a very long word to type out. There are 5 characters in it. It would be nicer if we only had to type 3, so we'll rename the parameter to num. Parameter names don't contribute towards the ABI. Nothing needs to be rebuilt. That's kind of nice. Do something, string, we've changed the parameter type now. The parameter type has changed. That has caused the signature, the ABI, to have changed. And so a recompilation is required of everything that's there. And finally, we realized that we shouldn't be logging to standard out. Logging to standard out is obviously a terrible mistake. We should all be logging to standard error. So we've changed the body of a method, standard error, println, the ABI remains the same. That doesn't contribute, right? So that's one of the reasons why you can sort of drop in a new updated point release of a jar and everything works, right? You don't need to recompile everything, it just happens. If we were to add an additional method or remove a method, that would cause our ABI to change. The JLS actually says that adding a method doesn't cause a change in the ABI, but we go like, actually, you might have changed a method overload or something like that. So we're going to cause a recompilation. So Buck has got the sort of language-aware smarts scattered through it for Java. Buck also supports, some of you are Android developers, I take it. Yeah, nods, like one person, two people. Good, excellent. So you've got some native code, possibly. We are extending the concept of this ABI stuff toward native code and generalizing these ABI keys that we're having to input source keys, which allow you to go like, hey, look, although I've overspecified all the headers that contribute to this file, these are the ones that I actually referred to, and because they haven't changed, you don't need to do a rebuild. Things like that. So this is an idea that was originally Java-specific, and we're now rolling that out through the rest of Buck. Exopackage. This is how we manage to get bits and pieces onto the device as quickly as we do, right? That redeployment of Messenger to the emulator was unbelievably fast, right? The main idea with Exopackage is to exclude key parts of the app from the APK. The thing that's super slow when you're installing an app or reinstalling it is transferring the APK backwards and forwards and getting the package manager to register that and do all that stuff, right? If you could keep the APK super slim and only update that very occasionally, then you could sideload the various bits and pieces you need, right? So the key idea is we exclude key parts of the app from the APK, install them directly to the device via ADB as secondary dexes, right? So incremental builds update the secondary dexes. We sideload those secondary dexes, and we just need to restart the APK. So there's no reinstallation step, which is nice, right? Building APKs also takes quite a long time because things like AAPT, not particularly fast. There's a little grimace on the front seat here. It's like, yeah. So in order to make this work, what we need to do is we modify system class loader to allow application classes to be stored in these secondary dexes. And then we have a class called delegating application and application-like for apps that currently have custom application classes. So we can put this thing in pretty easily. These allow you to convert an application to an application-like, and then everything gets stored in these secondary dexes, and then use a thin subclass of delegating application as the real application type. So your APK is super, super tiny, right? And installation is almost instantaneous. When you come to deploy time, like Exopackage is a developer optimization. It's to allow you to iterate quickly on your code. When you do a release build, we actually build a single APK. We don't do the secondary dexes. You get the thing that you expected out of the end of it, right? The APK, as if you weren't doing all these fancy shenanigans. While we were doing all this work with Exopackage and our Android builds, we noticed that there were two sort of long poles in our builds. First one was ProGuard. ProGuard is a code obfuscator. Have you come across that? Yeah, ProGuard. It's amazingly fast. It's doing a lot of work, right? So, I mean, they're trying to do what they can. But when we profiled our builds, we noticed that ProGuard usage was quite large. So what we did is we optimized ProGuard, figured out where the performance bottlenecks were just by simple profiling, and then upstreamed those patches. And if you have the latest ProGuard, which I think is 5, you'll have the Facebook patches to ProGuard in there, which will have helped your build times. The other thing that we do is we have a custom fork of DX in Buck. DX is the thing that takes the Java bytecode and turns it into Android Delvec code, right? And it turns out there's a number of inefficiencies in DX. Notably that it keeps a whole bunch of state data in statics, and so you can't keep it memory resident. Our fork of DX that we use on Buck can stay resident in memory, and therefore whenever we're compiling from a jar file to DX, we can just use that version of DX that's running in memory. Because we don't start up a new JVM every time we want to run DX, we get a little performance boost. And because a buck build is incredibly finely grained, very, very granular, we're doing DX an awful lot, right? So this is a huge time saving for us. So Exopackage is really interesting. If you go to www.buckbuild, you can find out more information on how to use it. Ludicrously fast builds, that's what I promised you. Gerrit is an open source project. You can download the code yourself from Google Code. These are some comparisons. They made the jump from Maven to Buck. The build times that they had for Maven package, so skipping Javadoc and testing, so just building the jar file, took 6 minutes, 50 seconds. When they did the jump to Buck, the build took 2 minutes and 3 seconds. So it was about a third as long. And that gave them the time to also run all their tests, which took 2 minutes and 3 seconds. So in the time it took to do a build and run all their tests, it was still 2 minutes faster than the time it took for them to do a single Maven build. No-op incremental rebuilds. Obviously, benchmarks lie. I am the author of one of these build tools. Obviously, no-ops are going to be fast, right? Otherwise, I wouldn't be saying them. But even a minor change, right? It doesn't matter where it goes. The rebundling is very fast in Buck. But for a no-op build, Maven package in Gerrit took 4 minutes 44. Buck build took 2 seconds. So, we are significantly faster at that point. And if you were to run buckd and do time buck Gerrit, assuming you've built it already, so buck build Gerrit, and there's a no-op build, that takes half a second. It's outrageously fast, right? It's not just me making these numbers up. You can replicate these yourself by downloading Buck and downloading Gerrit and doing a local build on your local machine. If I'm being unfair, please someone come and set me straight. There's probably some new Takari magic which we could use in order to try and make the Maven builds a bit faster that I'm not aware of. But yeah, Buck is fast, stupendously fast. In fact, I had one of the developers at Facebook sitting next to me. And obviously, I work on Buck, and so my Buck version is different from everyone else's, right? And he was also working on Buck, and he's going like, "Oh, the builds of Android are slow," and then he switched to the stable version, which everyone else used, because he was trying to debug a problem. And he sort of looks at me and he goes like, "Is it meant to be this fast?" We also recently had one of our developers file a bug complaining that their builds were too fast, and they didn't believe they could be correct. Which is a nice situation to be in, although we had to spend a significant amount of time proving to him that the build was actually doing what we said it was going to do. So Buck, obviously, lots of you do Java, stuff like that. I've focused on Java in this talk. Buck doesn't just do Java, it does Android, Java, Python. Buck itself is invoked with a Python wrapper script. And so when we deploy Buck to the machines at Facebook, we actually build a single Python archive, a PAR file, a PEX file, which is a library released by Twitter. So we support Python, C, C++. Obviously, you need to be able to build your NDK code. That would be nice. We also do standard C, C++. Objective-C, if any of you are iOS developers, you might find that interesting. React Native, we just landed support for that as well. That's going to be super exciting, very nice. Are any of you French? Then you probably don't program in OCaml. It gets taught at French universities as like one of the functional programming languages. I think over here we tend to teach like Haskell, things like that. I've very seldom met people who program OCaml. But we have some at Facebook, and so we support OCaml. We also support D, because the maintainer of D is at Facebook, and he went, "I'll contribute some code." It's like, okay, I'll take that. Cool. So that is Buck, a ludicrously fast build system. It's open source. Download it, contribute. Patches are actually welcomed. We're a friendly bunch of people. That concludes my talk. We've got about 5-6 minutes left. I've got time for some questions if anyone wants to ask questions. Gentleman at the front.
Is it implemented in Java?
Is Buck implemented in Java? The bulk of Buck is implemented in Java. There are bits and pieces that aren't. So the wrappers, for example, the launchers are written in Python. We use nailgun in order to pin buckd and give you a nice fast time. So your Buck builds are almost instant.
Does the JVM startup time affect the build time in that case?
Does the JVM startup time affect the build time? No, because we use buckd, and buckd pins the running JVM constantly. So you actually have a daemon process sitting there waiting for you. I guess the other question is like, I don't know, does it play well with IDEs? Yeah. There is a Buck project command which will generate IntelliJ and Xcode configs for you, so you can easily just hook one of those in. We're working on improving that. Gentleman there.
Any plans to support Scala?
Any plans to support Scala? Patches are welcome. So I work at Facebook. Obviously, the languages that we need to support are the things that my team have been focusing on. That's what I get paid to do. I'm also the lead of the Selenium project. So we can build Selenium using Buck, and for that I've added support for Google Closure, Mozilla extensions, and cross-platform types and things like that. I've extended Buck myself. We don't have Scala code that we need to compile yet. If you'd like to send us, I am actually genuinely serious. Like, yes, Scala I know is like super, super hot. Like Scala and Clojure are the sort of big two JVM functional languages, right? And having support for those would be awesome. We are flat out trying to get our iOS story sorted out. It is incredible for iOS, by the way. We've slashed build times. It's going to be so cool when we finally explain how to make all this stuff work. Yeah, but if you've got Scala or you're interested in Scala support, come and have a chat. I'll show you how to write a new build rule. It's pretty easy. You could probably simulate it using we've got these things called gen rules, and a gen rule is a generated rule. It basically allows you to sort of blow an escape hatch and execute an arbitrary chunk of whatever it is that you need to execute, and then take the output and put that back into the build graph. So no Scala support yet, but if anyone's interested in working on it, come and have a chat. I'll take one from this side of the room.
The majority of our build time is not compiling of the code, it's actually running the unit tests. That's probably about 4/5 of the time. Do you do any dependency support for that, or is it just run all the tests?
So, in fact, why don't I'm just going to exit out of here. Let's make this a bit bigger. Now, if I do this, and I'm a Yosemite, do you think this is going to do the right thing? Excellent. Okay. So if I print the current working directory, you'll see I'm in. Can you all see that at the back? Do you want me to make it a bit bigger? A bit bigger. Can you see that? Okay. So we can obviously use Buck here. The root of the tree, like I said, is determined by this Buck config, which gives you a bunch of aliases. These are things that we could build. And we also have a Buck version, which is what allows you to pin your version of Buck, right? So if you update that Buck version, it will also give you the same version of Buck. So you always have a repeatable build. Like, you go back a year's time, you can use the exact same version of Buck that you were using back then. So what you can do is, I'll just clear that. You can say to Buck, if I can spell the word targets, can you give me targets of all the type Java_test? Boom, boom, boom. It's parsed that, right? So here are all the test files that I have in the Selenium project. And you'll see that a handful of them are called small tests. These are probably good candidates for... so let's just grep for small. And let's also run the HTML unit tests, because they don't cause a browser to pop open, and I can just run them nicely. Boom, copy. There we go. And so what I'll do is I'll do xargs Buck. buck test. So that will feed all the small tests in, and we're also going to run these. Okay. This is a clean build that we're going from. So there's a couple of interesting things here. I'm just going to reduce the font size a little bit so we see the thing. Boom. We have automatically parallelized the build. Right? We have detected that we can execute these particular things in parallel. This is compiling JavaScript. It's not the world's fastest thing, I'm afraid. It colors the build for you. How many threads does it run? It runs number of cores available times 0.25. So if you've got 8 cores available, there'll be 10 threads that are executing. The reason for that is actually quite often your builds are I/O bound. And so maxing out the CPU is a sensible thing to do. You'll see that it tells you how long it's been running, how many jobs it thinks it has to do. When it comes to running the tests, what it'll do is it will fire up for each test target. It'll create its own JUnit instance, and so it can run up to 10 kinds of Java tests simultaneously, and then it will output the results as and when they become available, which you will see in a few seconds once it's finished building this. Obviously, compiling JavaScript is a tedious thing to do, but we've only had 90 seconds. Normally in Selenium, using something that isn't Buck, this is something that will take 5 to 6 minutes. We've almost finished compiling the Firefox driver. We're compiling tests, and now we're running, right? So it's running all those tests in parallel at the same time. If I opened up the activity monitor, you could see all the cores going like, I don't know what's happened to me. That will take a while. I believe we are out of time. I'm going to stay here afterward, and you can come up, have a chat. I'd love to chat to you. I'll be around all the time. But thank you very much for your time, and have a great conference.